So good morning, everybody. I'm very glad to welcome you for this second day of the LCBAT event of the 4 projects, Sublime, Solidify, Safely Move, and Astrabat. So today we will focus this morning on the last topical session dedicated to sustainability and recycling. After, we will welcome the industrial speakers, starting by Vercor with Yannick Molmerit. And we will continue this afternoon with 6 industrial speakers. I'm very glad they could join us. And we will discuss about the material and cells upscaling and challenge, which is very important for solid-state batteries. As you could see yesterday from the project, it's not that easy, and we still have a lot of work to do before commercialization. So I hope it will be a very interesting talk. And we will finalize the day with a discussion on how the project meet the new regulation and market scenarios. So welcome to everybody. Also welcome to people online. And to start, we will welcome Maria Martinez. You already know her from yesterday. And she will moderate the session. Thank you.
Thank you, Yolande. So I will moderate this session. So this third topical session is related to sustainability and recycling. And the speakers will be Marco Bianchini, Maddalena Rugolo, Davide Burlone, and Christine, I will try to say the name properly, Stelmeister. So I will briefly introduce to you the topics that we are going to be discussing. So mainly we have divided in 2 big topics, sustainability and recycling. And then within these 2 topics, the first part will be related to sustainability of emerging technologies, followed by sustainability assessment in the LCBAT1 projects. Then we will jump into the recycling topic, and here we will provide first an overview of lithium-ion batteries recycling, and from there we will move to the challenges of solid-state batteries recycling and how this has been addressed within the different LCBAT projects. After all, so differently to what we did yesterday, where we had 1 speaker, and then afterwards there was a few minutes for questions, we have decided to have the whole session together, so you will go through all the information, and all the speakers will have the chance to introduce their topic. And afterwards, we will keep 45 minutes for discussion. So all the speakers will be here, and you will have the chance to discuss with them. Okay? So then, Marco Bianchini will be the first one presenting.
Good morning, everyone. Thank you very much, Maria, for the introduction. As just said, I'm going to talk about the sustainability of emerging technology. I'm representing today Lomartov, and for those who don't know, Lomartov is an environmental engineering SME based in Spain, and sustainability of emerging technology is actually one of our big focus. So I decided to focus this presentation to give you like a general overview, also trying to introduce the following presentations. But in general, I'm going to focus on 2 main things. Why we do this, why we need this, and then mostly the how. So I'm going to introduce some tools or some frameworks that we can use to assess sustainability, especially in EU-funded projects. So first of all, why do we need this? So if we focus on all different type of group of stakeholders which are relevant in this ecosystem, we do have first of all investors, right? So investors are fundamental in scaling up the technologies from lab to market even, and we have, for example, research funding organization. We have private investors, and it will be important for this group of stakeholders to do a more comprehensive assessment of these technologies before investing, for example. In the case of lawmakers, on the other hand, we have governments, regulators, standard-setting organizations, and...
Sorry, yes. We have a problem with Teams.
Okay. Sorry.
Very sorry. No, it's share. I will start again.
I'm sure it's adding some suspense to the, to the presentation. Thank you. Okay. So I was saying we have lawmakers, which would definitely benefit, or it's really important that they actually take into account future impacts to create forward-looking policy frameworks which will help scale up these technologies. Finally, we have tech developers, among which a lot are here in this room. And they usually already consider sustainability in the research, but it's really important to go beyond the regulatory compliance to be able to have like more sound value proposition when it comes time to scale up technologies. And finally, well, society, of course. So I hope it's clear why it's really important to assess sustainability, and we need to do it according to a three-pillar approach. So the environmental, economics, and societal. And if we see how usually it looks like a R&D cycle, right? We can try to here we have like typical TRL scale, right? And we try to divide the two main phases in this R&D cycle. We have the first phase, which is like less maturity in the technology. We have design, feasibility, proof of concept studies. And here, what we can do is already doing a pre-assessment on sustainability, okay, which goes in parallel with the exploitation counterpart, which is below. And here we have a main problem, which is data availability. We have very few data about the technology itself. And also, it's a very iterative process with huge optimization margins, right? On the second hand, we have the piloting, prototyping phase. And here it's where we have already less optimization margins, more data available. We can do already what's called sustainability validation, right? And finally, we can take all this data and put it in scale-up scenarios to see how it will look like once we scale up technology. So now we move to the how. How do we do that? What tools we have to assess sustainability? The first tool I'm going to introduce is the so-called, it's pretty new, it's the so-called safe and sustainable by design. So here we are going to assess from the very early stage of a project, we are going to assess the safety. First at material level, the hazard assessment, then we go to the processing phase, right, about human health and safety in processing the materials, and then into the use phase, right, if this has negative impacts on health. After this, we move to the environmental sustainability and then further on societal and economic issues. But this is not really a linear process, right? It's actually more in parallel and very iterative. And so just to give you an example of how we can do that in batteries, for example, this environmental sustainability screening is what we call a battery material scorecard, for example, right? We can assess the amount and the importance of these, the critical raw materials we include in the batteries, the costs, some LCA indicators even, some recyclability issues, and finally, also the scalability of the production process we are considering in our technological concept. The second tool is more related to the social side of sustainability, right? So I'm gonna go pretty fast through it, but it's really important that we ask, as a researcher, we ask questions on why it is important that we scale up this technology. What are the benefits, and especially what societal needs we are answering to, right? Just mentioning this is a multidimensional and multi-stakeholder type of analysis, right? And as you can see, we are gonna basically this tool helps researcher focusing and answering and asking questions about what's the problem and the solution we are proposing, right? What are the positive impacts this solution has? What are the stakeholders which are mainly affected by this solution? And finally, what are the risk or mitigation strategies we have? So it's important to consider societal acceptance of the solution. So finally, we move to the second phase of these projects, right, of R&D cycle. We have the prototyping, piloting, scale-up phase. And here, we have enough data most times to already do what's called LCSA, which is life cycle sustainability assessments. This includes the three pillars, as I mentioned before: life cycle assessments, life cycle costing, social life cycle assessment, right? all of these three frameworks, they mostly follow similar type of methodology, right? Which is here represented. We have first the definition of the goal, the scope, and especially the boundaries of the studies we're gonna do. Then we are gonna compile all the data about the processes and the materials and so on. So it's this mass energy balance, which leads to a life cycle inventory, right? If we don't have primary data, we can always use other databases, which have mostly for environmental and social issues. Then we will we'll do impact assessment, right? And finally, we will do an interpretation of the results with sensitivity analysis, uncertainty analysis, and so on. So here, just to mention, it's important to try to standardize the method so we can compare all these type of studies, right? Especially because they're all comparative assessments. Right? This is more beneficial or has less impact than, okay? And also to identify finally what are the hotspot and main trade-off of the technology we propose. Finally, what's also very interesting is to project these assessments towards future scenarios, right? How it will look like, the impact of my technology when I scale it up, when it's on the market, and so on. So we can do it on the left. We have on the environmental side what's so-called ex-ante LCA or prospective LCA. So basically, here we can mix our foreground data, right, which is the data which tech developer has control on, the lifecycle inventory and so on, with other background data, which are usually, for example, collected through a pestle analysis, right, which are like the data related to our ecosystem around, right. We create these scenarios, and finally we can do this projection towards what's called forward-looking impact assessment. Something similar we can do with life cycle costing. If we don't limit it to a simple analysis, we can try to project it to how what it will look like, right, to scale these batteries, for example, towards sustainable gigafactories, right? That was our approach in Astrabat, for example. Right? And ideally, this process works starting from lab protocol, then we scale to a pilot plant design, right? And then we collect a list of all the equipment we need, the sizing, right? And this is always best if we have a expert partner like we have in Astrabat with our colleagues in Leclanché. Then finally, we can assess what's the whole CAPEX, OPEX, all these economic parameters. And finally, to compare it with a future market uptake, right? Will this cost structure will be okay to scale technology with good price. So to conclude my presentation, I just wanted to show you what the 4 projects has actually done so far. So and how we do what are our similarities and what are our main differences in our approach. And if we have the 2 main phases of the R&D cycle, right? We have in the early phases with Astrabat, we did these eco-design guidelines, and partners like Sublime and Safely Move, they studied already in advance possible recycling pathways for the batteries. And then finally, all the projects conducted in LCA, right? Most project and LCC. And finally, Astrabat is also trying to tackle experimental recycling to assess what would be the recycling efficiency with common recycling technologies for these batteries. So with this, that's all, and I'll leave the floor to my colleague Maddalena.
Okay, hello everyone. I am Maddalena Rugolo. I come from Gemmate. I personally worked on the Solidify project, but now I will kind of introduce the part of how the sustainability was assessed in the different projects and kind of the methodologies that were used and how they differed from each other, and instead how they were similar. So here is kind of like
more in-depth description of what Marco was just saying in the last slide, just to kind of visually understand how the different projects were kind of similar to each other and where they decided to use a different strategy to assess sustainability. I divided this here in the different phases, let's say, of the sustainability strategy, starting with the design phase, in which only one of the projects actually addressed sustainability in the design phase, going to the sustainability assessment, both to understand and study environmental and economical sustainability, end-of-life study, and therefore study of the possible recycling scenarios or an experimental recycling scenario, as Marco was saying, and then the scale of the assessment that was similar in most of the projects and different in just one of the projects. So starting from the design phase, the main tool that was used in understanding or addressing sustainability in the design phase was this streamlined, which means simplified LCA, combined with a functional analysis on just the step of the manufacturing of the technology, and therefore a cradle-to-gate analysis. As I was saying, only one of the project addressed sustainability in the design phase. This tool allows to preview the impact hotspots, so those spots of the technology development that will have a bigger impact over the other spots, and it helps guiding design and development of the technology. In this case, this eco-design was carried out only on the manufacturing step, but in other cases it could also be applied to all the other steps of the life cycle of the technology. All the other steps to the life cycle of the technology, such as, for example, the end of life or the use phase. The main challenge that developed from this part of the sustainability assessment was to ensure a beneficial trade-off between the technical and the sustainability requirements. So going to the sustainability assessment phase, most of the projects, or we can say all of the projects, used a similar strategy. So we carried out a full LCA, so a cradle-to-gate LCA, on the whole life cycle of the technology. The analysis was related to either a gravimetric or a function-related functional unit. And the results of the analysis were compared to a benchmark that was defined during the study, that in all projects was represented by a market-rated lithium-ion battery with a liquid electrolyte and an NMC-based cathode. In all of the projects, we decided to use an NMC 811 combined with a graphite anode cell. In one of the projects, it was used an NMC 111 combined with graphite cell that is what is already on the market. So going to the life cycle inventory, which is the main, the most important part of the assessment of sustainability analysis, we found out, sharing information between the different projects, that primary data was, so the data that comes directly from the experimental phase of a technology development, went into only the manufacturing step, so the building up of the inventory of the manufacturing step, while secondary data, so data that comes from literature or different types of knowledge, went into the build-up of the inventory of all the other steps. It is particularly important in this case to understand the role of the presence of an industrial partner, so an expert partner, in each of the stages that have to be inventoried in the analysis. In the cases of these particular projects, it was found out that in some of the steps, so for example the resource acquisition or the use phase, or even more the transportation, an industrial partner was not always present, and this makes a bit more difficult to collect primary data and therefore have a solid life cycle inventory. So going to the main, let's say, step of the life cycle of the technology, so the manufacturing, it was we found out that almost 50% of the data that was used to build up the inventory was primary data, so collected from the experimental phase, by different types of providers. So mainly cell designers and cell components manufacturers, and in some cases, lithium providers and the providers of the cathode active materials. The rest of the data that was used to inventory the manufacturing was secondary data, so data from the literature. This was necessary mainly for upscaling assumptions or to build up the inventory for those processes that are not directly addressed in the experimental phase or in the project in general. To make this secondary data more solid, it is usually necessary to validate the data. We found out that in all projects, the validation was carried out by an exchange of information with specific partners for each step. On the other side, none of the projects carried out a statistical analysis validation of the secondary data collected. So here goes to one of, say, the most interesting parts of the sustainability assessment, or the upscaling strategies that were carried out to upscale the life cycle inventory to an hypothetical industrial scale. We found out that most of the project had a similar approach to this upscaling that was actually a reverse type of upscaling. So not starting from the primary data and upscaling from there, but starting already at industrial scale. So trying to understand what is already on the literature, or which kind of data is already available for the industrial production of solid-state batteries, and working from there to kind of adapt this data to the information and the technologies that were studied in each project. So going to the results, we kind of try to understand which results were similar between the different projects, and in particular where the hotspots, the sustainability hotspots in each of the projects. We could generally say that the main hotspots were found in 3 of the phases of the life cycle of the technology, mainly resource acquisition, manufacturing, and end of life. For the resource acquisition, the hotspots were found mainly in the sourcing of particular materials, so mainly the sources of the polymers that were used in the production of the electrolyte, or the sources for other parts of the cell, such as, for example, the copper for the production of the current collector. We remind that copper is also a critical raw material, has been added as a critical raw material in 2023, as also other metals or materials that are actually used in our cells. Going to the manufacturing step, the main hotspots were represented by the drying of the electrode slurry and the use of glove box, mainly for, of course, the use of metal lithium, and specifically in those cells that were using lithium metal anodes. Going to the end of life, which was actually the main hotspot of concerning sustainability in all of the projects, and specifically the recycling efficiencies and the safety issues related to the lithium metal. So kind of to finish up, we tried to understand what was challenging and how the different projects overcame the challenges and therefore can help the other projects or future projects. So the main, one of the main challenges that was evaluated was the presence of a consistent number of assumptions throughout the inventory modeling, which lowers the accuracy. This particular challenge could be overcome by introducing statistical analysis tool to evaluate the secondary data collected. Another challenge was, of course, the related to the upscaling procedures or assumptions due specifically to lack of industrial data, as Marco was saying before, on the production of solid-state batteries, and particularly regarding the equipment for solid-state and related energy consumption. This particular challenge could be overcome by collaborating with industrial partners in the collection or modeling of the data related to the industrial production. Lastly, we found out that it was a small challenge was also the collection of the data from the partners of the consortium for each project. And this could be overcome by introducing a greater involvement of the partners in the decision making in building up the life cycle inventory, based mostly on trust between who has to give the data and who has to receive it to carry out the analysis. So just briefly, some improvements that could be introduced maybe in the next projects or in the second part of this project could be to include sustainability assessment already at the design phase, which I remember was carried out only in one of the 4 projects, as well as introducing recyclability efficiency at the design phase. And lastly, a need for an expertise for each stage of the life cycle in the project consortium that could help with collecting primary data on the whole life cycle of the technology. And thank you. I leave my word to Davide, who is here.
Good morning, everybody. I'm Davide Burlon from LCE, and I'm going to present you today a more technical part about lithium-ion batteries recycling. And I will go through the why we need recycling, so the need for recycling, how the European Commission, how the Europe handles this need, and then more technically about the state-of-the-art of recycling processes on lithium-ion batteries. So, why recycling? Actually, recycling can be an extremely resource and energy-demanding process. So, reuse and repurposing of batteries should be thought as much as possible. Let's say batteries have to be reused for stationary applications after being used for automotive purposes. But of course, recycling becomes an inevitable fate for every battery. So it provides then opportunities because it means that waste batteries can be turned into valuable source of raw materials. It allows to reduce battery materials production environmental impacts. Because like secondary materials usually have a lower environmental impact than virgin materials. It tackles the issue of raw materials depletion, and especially most importantly for the European Union, it helps to reduce the dependency on foreign countries regarding raw material supply. Just as an insight, almost 90% of lithium come from like Australia, Chile, Argentina, and cobalt 70% from Congo. So it is clear the need for European Union to focus on recycling. So how European Commission addressed the issue on 2023, like a few months ago, European Commission adopted the new battery regulation based on the old battery directive of 2006. That provides guidelines and regulations, obligations, both for the production of batteries and the waste management of batteries sold in the European market. Regarding end of life, so it clearly states that collected batteries at end of life has to be recycled. It sets collection and recycling targets, however, not indicating collection targets for automotive batteries, so that's a point that still remains open. And it indicates the minimum recycled content that has to be present in new batteries produced. So regarding performances and obligations, recycling performances and recycled contents are set in 2 stages. Let's say on 2025, obligations and 2030 obligations based on what is currently technically feasible right now and what will be technically feasible in the future. And on the left-hand side, we have the recycling performances, meaning the recycling efficiency of the whole battery pack, and a focus on the main materials, namely metals and lithium, that have to be recovered in a certain amount. Then we have the focus on like the presence of secondary materials, so materials recycled from previous batteries that has to be present in the newly produced batteries. So again, metals, cobalt, nickel especially, and lithium. The regulation also indicates some obligations to producers regarding the waste management of the battery, because producers are obliged to provide informations about to provide to users, operators, distributors, and to waste management operators informations about the state of health of the battery, the remaining lifetime of the battery, and most importantly, how to properly remove the battery from the battery packs so that it can be managed, reused, repurposed, or recycled properly. So, focusing more on technologies for recycling, it must be said that actually standard and proper recycling techniques are still under development. However, they are based mostly on like four different processes, and that are mechanical recycling, pyrometallurgical recycling, hydrometallurgical recycling, and direct recycling. By combining, let's say, these processes, complete recycling technologies and like chains are developed. Mechanical recycling. Mechanical recycling is basically the separation of all of the components of the battery that has to be thought more as a pre-treatment, let's say, of batteries, because of course it is not sufficient to produce new battery materials. So it has to be thought as a pre-treatment, but necessary, of course. Then we have the pyrometallurgy, which is a complete treatment of batteries, and it is based on smelting of battery and allowing to obtain a slag, a metal alloy, that is subsequently leached to obtain precious metals, valuable metals as cobalt and nickel, and by leaching technologies. It is a very flexible process. It is actually the most mature technology we have right now. However, except for materials, it doesn't recover any other material than like precious metals, and it is very high energy demanding process. So it has some downsides. Then we have hydrometallurgy, which is basically only based on chemical reactions, on leaching reactions to obtain, again, metals, cobalt, nickel, manganese, but also lithium in a way purer quality than hydrometallurgy, because it does not come from a slag. So hydrometallurgy is based on chemical reactions. It has a high flexibility to different battery chemistries, high efficiency of materials recovery, and most importantly, high purity of final products. However, it is very sensitive on the pretreatments. Pretreatments are necessary for this process, hydrometallurgy, because the more the various components are separated, the purer is the black mass stream, the purer are the outcomes and the quantity of the outcomes. It uses extensive amount of chemicals and produces a high amount of wastewater. However, it is considered right now as the best option for battery recycling because of a combination of efficiency, purity of the outcomes, and industrial feasibility. Then we have the last one, which is the so-called direct recycling, which is the most experimental one, which has to be thought about as a replenishment of used battery components, especially the active materials, because thanks to separation of different materials, some can be reused directly in other in new battery materials, and the active material, the active part, the cathode, by replenishment can be reused again. It has a very high potential, especially for like cheaper cathode formulations. However, is based definitely, its outcome is based on the state of health of the previous battery. So outcomes can usually have like generally lower quality because of the bad state of health of the previous batteries. To sum up, here you can find a list of existing plants at an industrially relevant scale. As you can see, many of them are from the EU, so it is clear the focus of the European Union on that. Just wanted to point out that the main recoveries are mainly cobalt, metals, nickel, and lithium in various forms. But all of them share like the incapability to recover electrolyte, organic components, and graphite anodes. So there is a lot of room for research also on that kind of recovery. So for me, it's everything. I leave the floor to Christine. Thank you.
Hello, and thank you. My name is Christine. I'm working in the Sublime project, and mainly on the design of a recycling process for the Sublime cells. And today I would like to give you an introduction to the challenges of solid-state battery recycling. I don't know, can I take control of this presentation, or should I share it myself?
If it's better for you, you can share yourself as you wish.
Okay,
Otherwise,
yeah.
I can pass the slides. Perhaps share like this, we can see you also.
Okay, yeah.
It would be better. Yes, we can see. That's perfect.
Okay. Good. Then, yeah, it works, right?
Yes.
Perfect. Then I will start with the short outline, what I will tell you today. First, I will give a short introduction into how we are working on to design a recycling process, so the different development steps. Then I will give a short comparison between lithium-ion batteries and solid-state batteries, and afterwards the challenges of the solid-state batteries we have regarding recycling. And in the end, I will have some possible recycling concepts we have worked out in the different projects here for our solid-state batteries. So first of all, the methodologies to investigate a recycling route. All of the projects started with a literature review on the recycling concepts that are already existing for common lithium-ion batteries. Why are we doing this? Of course, we try to find similarities, and don't want to start completely at zero, but find entry points, or maybe just process steps we have to modify for our new cells we are investigating in the 4 different projects. So all of us were starting at this point. Afterwards, some of us already did some literature review regarding solid-state batteries. So in some cases, there is already a little bit done and reported in literature, what we were, of course, looking at. This was the case for Sublime, Safely Move, and Solidify. And in 2 of the projects, Sublime and Solidify, we established then, based on all those literature review, a theoretical recycling model. And in Astrabat, they go even a step further and did the first lab scale experiments with their real battery material. After that, normally a process optimization would follow, and then in the end an upscaling before a process could come to industrialization. In our case, of course, we are far away from this because the cells are still in development, and we are not so far already. So there's still a lot to be done in the future. If we have a look now on the differences between lithium-ion batteries and solid-state batteries, we see some really huge differences and some similarities as well. One big difference is the anode material. So in common LIBs, we normally have a graphite anode, which is treated in common processes, recycling processes by hydrometallurgical treatment, or it is burned in pyro. In solid-state batteries, we don't have this graphite. We normally have a metallic lithium anode, so completely different. The binders, which are used to keep the active material on the collector foils, could be different. So in common cells, we have normally PVDF and SBR. And solid-state batteries, there could also be some other chemicals used. What is quite similar is the cathode material, as already mentioned before. All of the project has used NMC material. And then we come to the largest difference we have between LIBs and solid-state batteries. Of course, the electrolyte. In the common cells, it's an organic solvent, and in the solid-state ones, we have investigated in different projects. We have also 4 different materials. So we have sulfide-based, oxide-based, ceramics, and polymer-based ones. A very, very wide range of cell chemistries, which is also different to common LIBs, which are quite similar. Maybe the NMC material is a bit different, 111 or 811. But in general, the elements that are contained in the battery are similar for nearly all LIBs. This is not the case for solid-state batteries, which brings us already to the challenges of the solid-state battery recycling. So even LIBs are already multi-element systems, but I would say solid-state batteries are even more complex and even more multi-element systems. And this is always challenging in recycling because, we are in the best case, we are looking for all elements that are included in our battery, and the more complex the cell is, the more process steps we will need. Then we have the metallic lithium, which is extremely reactive, which also brings us directly to safety concerns and also to process control. So we will need maybe special facilities or special process steps to deactivate our lithium, that the further processing is even possible. Moreover, the lithium is very sticky, which can result in bad separation of the single materials we have in the battery systems, and makes the high recovery yields more difficult to reach. In case of sulfide-based electrolytes, we also have the safety concerns again, because they normally decompose. There's a decomposition with moisture very quickly, and then a release in toxic gases. We have to take care for this and try to hinder the electrolyte to decompose during our recycling process. What we also normally use when we are designing some metallurgical processes is thermochemical data, so that we can do first the modeling and find possible process windows. But in case of solid-state batteries, there is a huge lack of thermochemical data, so we are not really able to simulate something here, which will result in much more experimental work that is needed in the labs in the end. So higher workload. Then we have the binders. I already mentioned them. The cell manufacturers, of course, always want everything to be sticked together and have a long life chain. But for us recyclers, this is quite difficult because we have to remove them, decompose them, or maybe dissolve them in solvents, so that we can separate all the single materials again. Then we have the thing that different solid-state batteries may require different process steps. So this could be, especially when we think already bigger for industrial scale, very complex and challenging, because a recycler maybe don't want to have 4 different recycling routes or facilities because there are so many different cell systems. Yeah, and at the moment we have a lack of established processes in this case. And then last but not least, I would like to talk about the electrolyte recycling. In common LIBs, it is not done because there's also not such a high value of the electrolyte as we have it in solid state batteries. So here we should really care for recycling of the electrolyte. But this could be really, really tricky because they are normally composite materials and they will need very harsh conditions in hydrometallurgy. There will be a lot of work needed to come to new recycling concepts to recover also the electrolyte. In the next step, I brought a table where I tried to compare the lithium recycling process steps that are used for single components of the battery and what could be possible solutions for solid state batteries in comparison to this. So one component we have in both batteries are the casing and the collector foils. And in common LIBs, they are normally recovered by mechanical separation. So there is a shredding step and then sieving and shifting operations where we can separate the copper and aluminum from the active materials. And this could also be a possible solution for solid state batteries because this is quite similar. Maybe it is a bit more tricky to really come to good delamination of collector foils and separation, as I already mentioned, because of the metallic lithium, for example. So therefore we will need definitely an inert shredding and sorting process, and maybe before also the maybe a thermal treatment or something else to get rid of binders. Then we have the electrolyte. In common LIBs, this is normally not recovered. So there's, for example, a deactivation in thermal processes where it is just burned. And this is why it's normally not industrially recycled yet. In case of solid state batteries, we have to decide for every single system we have for possible process rules. So in case of sulfate-based batteries, it could be possible to recover the electrolyte in an ethanol solution because it is very, very good soluble in ethanol. If we are able to keep it in its normal state, so the electrolyte, then this could be a really good and possible solution. For the oxide-based battery cells, and recovery by leaching and precipitation could be possible. And for the polymer-based, we still have a big question mark in our head, so this is not really clear yet. It seems that this will be quite difficult to recycle. For example, if we have a thermal treatment step in our recycling chain, it could be quite similar to normal LIBs, that it decomposes and could be kind of lost in the off gas we are producing during our processes. Then we have our lithium. In common LIBs, it is normally in an oxidic form together with the other metal oxides, and therefore it is normally recovered by leaching and precipitation steps, so hydrometallurgically, which is at the moment not industrially implemented, but we know that companies are working quite hard on this at the moment. In the case of solid state batteries, we will need a phase transformation of the metallic lithium before. For example, it could be in a thermal treatment step together with CO2 that we form lithium carbonate, which could be then leached by water. Otherwise, if we don't transform the metallic lithium to a salt before we go into hydrometallurgical steps, we will have uncontrollable reactions, and I think our process would collapse. And for the NMC, in the end, for common LIBs, we have leaching and precipitation, so common hydrometallurgy. Or if we go the pyrometallurgical pathway, we will collect it in an alloy by smelting. In case of solid state batteries, most of the projects came to the conclusion that we will end up with the leaching and precipitation step to recover the NMC. And Now I would like to show you some drafts or outlines we have done in our different projects for our different solid-state battery cells, how a possible recycling chain could look like. So here we have the example for Sublime, which are the sulfate-based electrolyte cells. We thought about first an inert shredding step to separate the metallic fractions, except of the lithium. This will be transformed to lithium carbonate by a second step, which is a thermal pretreatment under CO2. And then we thought about a recovery of the electrolyte by ethanol leaching. Second, the lithium recovery by water leaching, if we were able to transform it to lithium carbonate before. And the last step would be the recovery of the NMC by common acidic leaching and afterwards precipitation or solvent extraction. And yeah, this was a completely theoretical investigation, but the comparison with lithium-ion battery recycling processes and theoretical calculations promised to meet the European Union requirements for recycling efficiencies in the future. Now we come to the ceramic polymer-based electrolytes from Astrabat. Here, real experiments were carried out with the established cells. So first of all, they were mechanically treated to separate the black mass. And here, two different pathways were studied. So the first one is a smelting process of the black mass, where the metals were collected in an alloy. And the second one is a hydrometallurgical process step, where first a leaching in sulfuric acid was carried out, so that we have a solution where all our metals, copper, nickel, manganese, cobalt, lithium, and aluminum are contained. And this solution goes into an ion exchange chromatography process first. Here, copper, nickel, and cobalt were extracted selectively, and with purities of more than 98%. And from this process, we end up with a solution which still contains aluminum, manganese, and lithium, which could be then selectively precipitated afterwards by common hydrometallurgical process steps like pH value adjustment. Yeah, and now the last one is the case study for polymer-based electrolytes, which was done by Safety Move and Solidify. Here the process starts, or the theoretical process starts with the dismantling and discharging step.
Are you connected, Jolan? Maybe you can. I don't have a microphone. No, but maybe to put in the chat, because maybe she's still talking and she doesn't realize that. Yeah. No, it's Christine? Okay, so this is Maria. Sorry, so we had an issue in the room, and you got disconnected just when you changed the slide. So we got disconnected. So you are connected. The issue is coming from the room. So we saw already the results for Sublime and Astrabat, and then we are missing the last two slides. So give us a couple of minutes. We are trying to fix the issue in the room. Okay. Sorry about that. No problem. Just tell me when I.
Scarlett, on est bon. Ouais, et du coup, la caméra, on a bien celle-là aussi.
Okay, we are back again. Do you hear us, Christian?
Yes, I hear you.
Okay, perfect. So you can continue. Sorry, I think we missed the two last slides.
Yes, two last slides.
Thank you.
Yeah. Okay, yeah, then I will just repeat what I said about the polymer-based electrolytes. So here we have also a theoretical recycling concept worked out by Safely Move and Solidify. The process starts with the dismantling and discharging. Afterwards, there's the pre-treatment to break down the polymeric portion of the electrolyte before the material enters hydrometallurgical multimetal phase treatment to recover the active materials. Here it is at the moment not really clear what will happen with the polymer electrolyte. This will have to be worked out in the future and maybe one day also with real lab scale experiments so that the circulation of materials for resynthesis of a new battery cell can be closed for this polymer-based electrolytes as well. So then I will quickly repeat the outcome we have here for the solid-state battery recycling research. Until now, we have nearly just theoretical investigations and some small lab-scale experiments in Astrabat. So what we need to go further is more thermochemical data that we can first have some deeper theoretical investigations in our recycling processes and define process windows. And when we have a sufficient material amount, go into our labs and do the real establishment of recycling processes by experiments. And our goals here are, of course, an extensive process development. It would be really nice to find entry points into already existing lithium-ion battery recycling rules. I think this was also already shown in our recycling concepts. We try to stay close to already existing lithium-ion battery recycling concepts. And yeah, we are all aiming for a near zero waste concept, that we don't produce too much wastewater, try to recover nearly everything from our battery cell as far as it is possible. And what would be really nice, as we are also sitting here with the cell manufacturers, to give some hints for a design for recycling, that the cells are directly designed for an maybe easier decomposition and chemical recycling process in the end. This is all from my side. I thank you very much.
Thank you, Christine. So may you stay with us now for the roundtable discussion?
Yes, of course.
Okay, so I would like to invite to the table to the speakers. Nice to meet you in person. Okay, so we have around half an hour for discussing about sustainability and recycling topic. So please go ahead and bring your questions or any topic or curiosity that you may have for the different topics as well as the different projects. I will take one of the microphones to share with the audience. No? Yeah.
I have the question for the first speaker. You mentioned something related to eco-design. I was just wondering if you could share some values, because I saw methodologies. Do you have some values in terms of absolute values or percentage comparing the technology of the project with classical lithium-ion?
Um, Thank you for the question. Not sure I can really share any values. I just wanted to point out that this type of stage is always, it's hard to compare also in a sense, because we are assessing still a technology that has been developed at a lab scale, right? So the difference between lab scale to a real industrial scale in terms of impact is really huge, because we have the use of glove box, we don't have recovery of solvents in many cases, so the impacts are maybe 10, 100 folds compared to actual industrial scale. So it's hard in that sense to compare. And yeah, I think some of the bottlenecks, the main bottlenecks, were actually included in one of your slides, I think it was. So for example, we noticed the drying of the electrodes was probably one of the most impactful stages. So it's something that we actually interacted with the materials developers and the battery developers in the end to try to address also these issues. But besides that, I'm not sure if I can comment more. Thank you.
But my second question is on the bottlenecks. When you say it's a bottleneck, what is the metrics to say it's a bottleneck?
Yes, so we are actually comparing these to traditional batteries also in that sense. But so we always have to try to scale down to have a more comparable analysis, right? Because in the case of literature studies, most cases also on real batteries, right? On real also scaled up batteries in that sense. So yeah, I think this is one of the bottlenecks is what I mentioned. There are others related mostly to solvents, for example. In a specific case of Astrabat, yeah, I think it was mostly about solvents. The main difference we don't have only an NMP. We have three types of solvents also in our process. So that's also a bit of an impact we have considered, for example.
As you know, Safely Move is the only project they don't use copper as collector. I would like to know if you help us through your calculation energy consumption to produce this anode, which is more advantageous to have more thicker anode of lithium, freestanding lithium, or having thinner with copper.
Well, I can speak only, I only did the analysis on the Solidify battery, so I can kind of speak on what we had as results. I'm not sure if you did an analysis like that, but no. I would say it is from a sustainability, from an impact point of view, it would be a higher impact to have a copper current collector compared to a, depends on the thickness of the current collector. So if we have a thicker copper current collector compared to the lithium one, it would have a higher impact. But this also, when we say it has a higher impact, it's also, it depends on what we're talking about. So if we're only talking about manufacturing, then it could have a higher impact. If we're talking about the whole life cycle impact, then if the current collector affects the use, for example, phase of the technology, then this result can differ. Or also, it could affect the end of life. So if copper is easier to recycle compared to lithium metal anode, then this again impacts as a different impact. You know what I mean? So.
In all cases, I mean, except lithium-ion, I don't know which project using lithium-ion, but for the other project, three project, all cases they use lithium metal. So when you added copper, it means you added another process to recycle, because you will recycle lithium and copper. So we will have more cost, addition cost to the recycling process.
So you mean you don't use any copper? Okay, no. Okay. Yes, then it could have a lower impact. Sorry, I didn't understand that at first.
Good morning. Thank you for this presentation. I have a question because we are speaking from 4 different programs in this symposium, and I want to know if you use the same KPI to evaluate the environmental impact or the LCA, etc., from each project, because it's I don't know if there is a real standard on that, but it's quite difficult to compare different indicators. So I would like to know if you know which kind of KPI you use in each project, and if they are the same or not.
Should I answer? Okay.
Not sure. Didn't talk.
I think, I mean, we haven't talked about that. We haven't talked, but of course we are addressing, I mean, global warming potential, of course, that is the one that is being addressed, I guess, by everybody. But yeah, there are no, I mean, there are standards, but there are no like specific standards on batteries. So it is more on what we think the sector requires an analysis on some specific environmental aspects. So there is not a specific standard that tells us you have to address this environmental impact. There are, of course, methodologies that allows the calculation of various environmental impacts about different, I mean, environmental indicators, eutrophication, acidification, photochemical ozone creation, and many others. But yeah, it is more a choice of the analyst. So.
Just to adapt something that I mentioned in my presentation, that's so the need for standardization in what type of methodologies we are using. It's out there, so it's something that the European Commission is addressing right now. So, for example, they recommend the use of this environmental footprint method that they have, but so far there is no real like. We are actually entitled to choose the methods we prefer. So in most cases, the ISO standards are mostly followed. And yeah, then for the rest, you compare according to the categories which are mostly important for this type of technology. For batteries, of course, global warming potential, use of raw material, resource consumption, and so on. So yeah, in the end, you try to have these comparable metrics between projects.
Thank you. And second question, quite fast. According to you said that it's quite difficult to have some input data coming from industrial or raw material, etc. At the end of the project, do you think it's possible to share this kind of data to avoid to restart from a white page on another following project?
That should be a question to ask maybe the industrial partners or the other partners. I think we have to discuss maybe among each project which kind of data could be shared, or maybe just the results of the impact analysis could be interesting to share between each other, just to understand, as you said, where we are at and not to restart again maybe in the next projects. That would be really interesting and really appreciated also for us, I guess. Yeah, thank you.
Again, just to adapt, in the case of Astrabel, for example, the life cycle assessments and life cycle costing studies will be public, but the approach you follow not to disclose, for example, confidential data is like this black box approach. So you don't really say how you get there. You just show the end results, which are like normalized. You cannot really retrieve, where you take it from. So.
I have a question about the recycling rate. You said that some components were not recycled today. So today, do you know the recycling rate of batteries? And also, do you know the rate of recovery of lithium-ion batteries from the market?
You mean as like volumes of...
Percentage, yeah.
Okay. Actually, no. I don't have this data. I know that there are like some plants, some industrial plants that can manage, that can handle like several like thousand tons of collected batteries. So it is like a kind of relevant amount already. But actually, the share of batteries, it is not something that is actually easy to have right now as a data, because the high volume of waste battery will come in the next years, because of course especially like electric vehicles, are being sold right now at the moment. So we will have some like strong data more in the upcoming years, I guess. More or less, we have like vehicles lasting, I don't know, 10, 15 years, 10 years. So yeah, it is, still a bit early to have like share of market shares about collecting.
And do you have information on the real actual recycling weight in weight of battery which is really recycled today?
No, actually, at the European level, I honestly don't know what's the level or what we have achieved so far. I think like most of the efforts are very recent, and even the need for recycling is sort of recent. So we just hope it's gonna be more in the coming years. Yeah.
Okay, thank you.
Thank you to all speakers for interesting panel. I have one provocative question to all of you. So I saw you're a bit like reactive. So you say, so those guys, they develop something and we have to think how to recycle. So in this case, my question, what would be ideal solid state battery for you from your point of view of recyclability, sustainability? So can you make some reflections on this? For example, yeah, we know that we don't need copper, yeah? So it's one point, but maybe, I don't know, some reflections on materials, maybe binders, maybe, I don't know, some, like what, because for us it's also important because I think about performance and safety, so I don't think about sustainability at the first glance. And of course it is not, let's say, the way for current situation to think, but it's difficult for us. So then any recommendations or thoughts are welcome. Thank you.
Maybe Christine.
Yeah, I think this is a really tricky question because the needs we have, I think the cell manufacturer and the recycler are differing a lot. So for example, we want a cell that is easily, that you can easily decompose into different components, for example, by a shredding process. Of course, the cell manufacturer wants that everything sticks together safely over the lifetime of a cell. It is, for me, hard to say which binder you should use because I'm not so deep into possible solutions except the ones that are already on the market. I can just say that it is hard for us to, for example, treat a binder that decompose at very high temperatures. It would be much easier if we just need, for example, 200, maybe 300 degrees compared to 550. We need to get rid of PVDF at the moment in common lithium-ion battery recycling. This is something challenging. Also, the more complex the battery cell gets, the more elements are contained, the more complex also the recycling chain has to become, because of course we try to care for every single element in a battery cell, and we will also be forced to do this by the European Union to meet the requirements they are giving us. So for us, the simple, keep it as simple as possible would be a nice way, but of course you have to meet requirements regarding performance, etc. We know that. So I think this is really difficult to answer so shortly. Yeah.
Thank you.
If I can add on this, like for what I found from my analysis, so it is important that what has a very high impact at the beginning, so at the manufacturing step, can be also recycled almost completely and in a easy and safer way. That's like what actually works out at the end. Because, for example, for us, like in our electrolyte, we had some components that had a very high impact, but can also be recycled at the end, and so these impacts kind of cancels out in a way. So that is something that to keep in mind at the design phase.
So my question is maybe going in the same direction, and is regarding the recycling of the polymer electrolyte. So we're having 4 projects, and all 4 projects have different chemistries and different approaches for the polymer electrolyte. And my question is, it's difficult to recycle the polymer electrolyte anyway, and this huge variety of chemistries, of course, doesn't make it easier. You think it would be better if we align in some directions and make some standards in terms of the polymer architecture or the polymer chemistry that would help to develop an actual recycling process?
Yeah, thanks, Timo. Yeah, you're right indeed. I think it's somehow polymer is one of the most challenging also to recycle. And I think that would be very, very useful and should be supported by experimental results as well. So we know better what works, what doesn't, in order to achieve the best results. So I think it's pretty early maybe to say that. But in the future, I think it would be super useful to be aligned on this. You know, in terms of like amount of polymer, architecture, way of recycling. That would be very, very nice. Yeah.
Just to add one thing, I mean, currently recycling at industrial level is a bit complicated because there are a lot of different chemistries, a lot of different like typologies of batteries. So that's what actually hinders also the development of a recycling like infrastructure. So of course, like standardization is to be like pursued, but actually being a research state, it is. I mean, we have to explore all of like kind of possibilities, but of course, to have standardization would be good for like industrial development, of course.
Actually, I think, so combining Timo's comment with the one from Andre, I think if we will have, for example, for the polymer side, that is the unknown component to be recycled, if we could have some standardized protocol already, this will allow to the people working on the design of materials to tune the properties in order to make it recyclable. For example, what Andre was asking. So I think if we have some hints at material development level on how should be the material to be later recycled, will be also useful. No, designing something that really you cannot recycle. And I think this is something that we learned in Safely Move, not with the recycling, but with the processing. So CIC is more at material level, and then when we transfer to CDTech, we learn that this cannot be so easily scaled up. No? So because we are focused on performance, I don't care how this is scaled up. So I think that here we'll apply the same. Maybe now we are on an earlier stage to know because which is going to be the winner chemistry, no? That deploys the use of solid-state batteries, but it will be also nice to have this kind of loop. So from the very beginning, design or at least know somehow how this will be recycled. And also I wanted to ask to you, so to all of you mainly. So I was thinking when I was seeing the presentation mainly from Christine and also yours, so we don't know how polymer will be recycled, but for example, if we consider that this low-cost component, I was thinking, what is going to be more valuable if at the end this is going to be a very costly recycling process and also is going to consume energy, so this will have a footprint impact. So I was thinking, what will be more important? So because I'm not familiar with this LCA and the sustainability topics, but I know the new regulation, but at the end, I think we need to consider not only fulfilling these KPIs by mean of percentage of recycling, but at the end, maybe I recycle this, but then on the other hand, I have an impact that at the end impacts on the sustainability. So I don't know. What are your thoughts on this regard?
I think, I mean, it is important to understand, to have in mind that the trade-off, of course. You can also obtain polymer from, I mean, a lot of other various chains and so on, while like lithium and like kind of that materials come only from, basically from nets, so from batteries. And also yeah, the amount of polymers inside the battery is usually lower than other I mean, can be lower and less relevant than other materials. So of course, we should think of a trade-off. That's of course, and to have perhaps a driver in mind and to pursue that driver. But yeah.
What is also, I think, important to keep in mind is also at kind of market level, and it is also what we were trying to do with developing the the recycling scenarios for the different technologies. It would be easier to keep the recycling scenarios very similar to what already happens with lithium-ion batteries with liquid electrolyte, and maybe adding, if possible, one step or few steps that do not have a high impact, as you were saying, a high environmental impact. And it's easier because, of course, the facilities are already there. You just have to add like a small, let's say, process. And also from an environmental impact point of view, it would be better to just have a small impact that cancels out the impact of manufacturing the material again. Of course, as you were saying, if the recycling is more as a higher impact compared to the manufacturing of the element, then it's not sense to do it.
Okay. Thank you. So at the end, I think that the suggestion that you were saying, Madalena, will be aligned with the learning yesterday from, I think, was Andre the one saying. So if we can use a facility that already exists for lithium-ion, the transition will be easier, faster, and
repurposing also that.
yes. Okay.
Yes, maybe my question was, do you think all these issues about environmental impacts and recycling are related with high energy density targets? I mean, do we really need such energy densities for our mobility applications? Or the other way around, if we had a lower energy density battery, would it be easier to recycle and manufacture and make it circular, even if we don't go to 200 kilometers per hour, for example? Or maybe, and then I stop. Energy density is not an issue. Is not an issue because anyway we need to meet some chemistries and some technological approaches and processes. But I'm interested in understanding this because maybe we don't need such high energy density to go around with our cars, as most of the time we go, I don't know, 50 kilometers per hour.
Yeah, that really depends on the use. Like the use phase is also an important part of the life cycle, of course, of the technology, and also for the environmental impact analysis or economic impact analysis. Yeah, there is a trade-off between the two things. So it also depends on how you are supposed to use that particular technology, for how long. Energy dense, if we have a lower energy density, maybe could mean that we have a bigger, like a higher quantity of materials, and that could mean a higher impact. So it really depends on a lot of things, really. And I think the main point is where and how we have to use that specific technology, and then work from there. So from the use phase and then work from there. I don't know if you agree.
Yeah, I mean, I agree. And I also think that researching into a solid-state battery is not just about increasing energy density, right? We're improving safety. Well, then, of course, energy density, as you mentioned, also affects what's the impact of the battery in the end, because if we think of the impact normalized to the energy density, the higher it is, the lower is going to be the impact. So I do not think it's just about the use phase, but it's also everything that entails having this sort of batteries, which are like safer, of course, can be more powerful, better, adaptable to different applications. I think it's a bigger discussion. Yeah.
Okay. I think, Aras, did you want to ask something? I think you did like this, or no? Okay.
One question. I think we all saw that was not very simple to determine what is the production method for upscaling the technologies that we're touching in the different projects. what was your strategy to analyze that in the life cycle? And what's your opinion in how to handle this subject? Is there a big impact in choosing one technology for the analysis there, or this is quite relaxed in terms of what is the outcome of the study?
Just a very quick answer from my point of view. For the upscaling, the most important thing is what data you have, right? And it's not easy to get data about upscaling. So it's not really about the method you use to calculate or anything. It's most about what data are available and you can have access to, especially in a very highly competitive environment as it is battery manufacturing, I think. Then, of course, it's also pretty important, the upscaling phase, because it's where all the costs, then matrix will make sense, because at lower scale it doesn't. It's simply it's a business with very low margins, so you need the best upscaling way, let's say, to achieve that cost reduction. And just
yeah, I think for me the most the best way to kind of like do this upscaling is try to have the most standard scenario in the future, because we're actually upscaling to scenarios that are probably in the future, are hypothetical, they're not there yet. We don't have the data yet. We have very few data about the industrial production on solid state battery, and that is the main source of data we use. For us, for example, in Solidify, we had the help also of some industrial partners that we had in the consortium. We spoke to them. We kind of we were trying to understand if what we found on as secondary data was actually if it made sense for them. It was also difficult for them to understand this. So I think that the best way would be, there are different ways to do it, but the best way would be to make the most standard assumption. So what will be standard in the future, and then use that as your upscaling scenario.
But if you just focusing this industrial process that doesn't exist yet, and you need to take something standard to be able to judge, in your opinion, is this like a critical factor there, or it doesn't matter so much at the end of the calculation?
I think it matters a lot. I mean, it is very important, and personally think that it will be great to put more effort, like in the proposal of the projects, like to have more effort in the kind of upscaling of that processes. I mean, not only like understanding if it is feasible at lab scale and research on that, but also like put some effort in understanding how industry can be developed. Because for as Marco and Maddalena was saying, like calculation of environmental figures really depends on that, because data results calculated on lab scale are very completely not representative, because I mean of the scale, basically. So it is critical.
Also, just like connecting to what Andrei was talking about yesterday, so the importance of having a manufacturing way that's closer to what we already have, right? So, for example, in the case of Astrabat, I feel that maybe not having lithium metal, the manufacturing can get closer to what it is, the current manufacturing processes. So this allowed us in this upscaling task, for example, to use models that already exist also for the modeling, right? And for example, the backpack developed by the Aragon National Lab, and it's something that it's never going to be perfect, but it's already a very nice starting point, and you can give you a pretty nice idea of where it's going to be, right? So.
Maybe I can just complete something else. Sorry. The life cycle assessment, it's pretty complex and quite long, taking into account many different aspects. And just to come back to what Christian was talking, what is the impact, for example, of decreasing 200 degrees in the pyrolysis of a recycling plant? Is this really impactful, especially touching the point in terms of the performance that we bring, right? Is it important, really? It's
I think
important
yeah.
for people that are building recycling factories, that for sure. But if you take the complete process,
yeah, I think generally speaking, everything counts, because in the end, it's always like impact reduction, and then depending on the scale that you're looking at, it can be upscaled also that impact. Then of course there are. So I think the purpose of the tasks we also carry out is like to identify which are the hotspots, so you can see where it's better to take action. There are some things that maybe you cannot really change. Maybe you cannot reduce those 200 degrees, but maybe you can reduce one step. You take out one step in the recycling process, and that's, of course, for the manufacturer, as you said, it's like cost benefits, it's like less work to do, and there's less impact in many cases.
Maybe, Christine, would you like to add something?
No, I think it's really good said already.
Okay. Aras.
Yeah, thank you very much for the nice talks. I just have a question regarding the recycling of these solid electrolytes. So at the moment, solid electrolytes are more expensive than liquid electrolytes. But then you show that, for example, for sulfide, you can recycle them, and then it works in favor of, for example, reducing their cost, the overall cost. So, I mean, yesterday, for example, it was shown that ionic liquid works very well, but the cost is high. So it is stable versus lithium metal, high voltage cathode, but the production cost is so high. So may I ask if you have any idea if this could be recycled in the process you showed, or it is also like polymers and it is somehow impossible to get it back?
This is actually an issue that we are trying to tackle right now in Solidify, because we have the ionic liquid in our electrolyte, and it is one of the main actually tackles. As I was saying, also because not only the economic impact, but also the environmental impact of ionic liquid is pretty high. So what we're trying to do is try to find the best solution to recycle that and maybe lose the polymer. So that is what we were saying before. Maybe you have to lose some things, but then you have to be able to tackle the most impactful things, like elements inside your technology, and ionic liquid would be.
So there are some ways to recycle it.
Not sure yet. I cannot answer you right now, but we're studying into that, and probably there is. We still have to understand how to do that in the context of recycling the cell, the battery cell. Yeah.
Thank you very much.
Okay. So we are just on time. So I'm really glad, because there was many questions. Actually, I wrote some questions and I didn't have the chance to make even one of them. So please let me thank again to the speakers. It has been a pleasure to prepare with you this session. You were super proactive. So thanks a lot for you again. Thank you, Christine.
Thank you.
Thank you. Okay, so now we will have a 30 minutes coffee break, and then we will come back with the, let me check, with the talk from Vercor. Okay, so for the people online, let's connect again at 11:30.